Well, good evening, everybody. I'm Charles Schultz, and this is the Randomizer for the 4th of March, Friday, 2022. Now, tonight we have an interesting topic. It is scatter. You wouldn't think you could say a whole lot about a simple word like that, but believe me, there's a lot of interesting stuff going on there. So we're going to get at that very shortly here. Be sure to visit schultzlaboratories.com or universesciencecenter.com. Go to the pages. Click on the link that takes you through to our sign up page, become a member, and support the growth of our galleries and content. Get your Oculus or your VR headset, walk around the galleries and explore and enjoy the things you see. Call your friends, share it with them, get some people interested in here. We're trying to make this simple and amazing educational system available to everybody, everywhere. Also, 9 p.m. Eastern Standard Time, we have our lessons, our regular classes. And this Monday, it will be lesson 6 of our technological story, the advancement of mankind from sticks and fire to nanotechnology. That's Meta World. Lesson 6, the conclusion, will be Monday. And that will be the 7th, by the way. Every weeknight at 6 p.m., as you're likely to know, you have the randomizer with a new technical term every time. And tonight's technical term, as I mentioned, is scatter. So let's get into it. So what is scatter? Literally, the definition of scatter is to simply impart random motions to a number of items. And if you were to take something like a handful of BBs and just kind of toss them in the wind, they would scatter. Every one of them would have its own distinct path and would end up in a different place, quite likely. So scatter is simply the term for randomly broadcasting something, a number of somethings in some direction. And now, how does that relate to physics? Well, we're going to talk about a couple of interesting examples. Everybody knows about the importance of the number pi in mathematics, and it is simply the ratio of the circumference of a circle, the distance around a circle, to the diameter of the circle. And so for any circle, and I'll just take the top off of my drink cup here as an example, if we were to measure the distance across this circle and multiply it by pi, we would get the distance around our circle. So the diameter times pi equals the circumference. Very simple. But that's a funny number, pi. It has a lot of definitions, and they all come down to one value. Many equations can calculate it, but pi is approximately 3.141592653. It's a long, never-ending, irrational number, which means there is no exact equation that gives you the answer. Actually, you have to calculate many, many terms. But there's an interesting way of finding the value of pi that has nothing to do with that. Let's say you had a field, and the field was an exact square. And from one corner of the field, you took a compass and you drew an arc, a quarter of a circle, filling that field. So if we were to do this on paper, you would have your square field, and you put a compass in the corner, and you draw the arc all the way down, trapping a quarter of a circle in your field. Now, we're going to have a simple rule. Anything inside the circle adds to the number I. Anything on the outside adds to the total number. And so you're going to end up throwing a whole bunch of darts at this property. And all the darts you throw will land somewhere on the property. And it's a very simple thing to see. You could drop a million darts out of the sky all at once, and they could land on this property. Now, here's the trick. You count up the total number of darts. Let's say it's 1,000,000. You see how many are inside the quarter of a circle. Just fell at random. Then you take that number divided by the total number of dice, and you end up with 1/4 of the area of a circle. And if you do this and divide by 4, you'll end up with a number very close to pi. And the more shots you take, the more accurate it gets. So it's crazy, but that's the way it works. The ratio of dots that fall within the circle as related to the big square will be pi. And the more shots you get, the better it gets. Now that's actually calculus, getting closer and closer to your answer with continued samples. But the samples are the key. You literally scattered it at random, and the value of pi is related to the area of the circle that you got there, and that's the answer it's going to give you. That's crazy. Randomly scattering a bunch of darts in a square field with a quarter circle in it can give you the value of pi. Who would have thought? Well, obviously somebody was smart enough to have thought that. All right, so here's another thing, scattering. Let's say I have a piece of metal foil, and I'm going to shoot a beam of electrons at it. Now, sounds like something stupid to do, but actually there's interesting things that happen when you do that. If you've ever had an X-ray at the doctor's, what they use is an X-ray tube, and the tube is basically a vacuum tube. And the tube has a filament in it, just like a light bulb, only it's not meant to glow up in light. It just basically is red hot. And that filament has the ability to emit electrons. Now, you will charge a metal plate in the end of the tube with some voltage, call it 10,000 volts. When the electrons come off of that filament, if the filament is positively charged, you won't get anything reaching the plate if it's positively charged, negatively charged. If you positively charge the plate, electrons are negative, and when they emit, they'll come rushing over to that metal plate. So the electrons are being spit out of the filament, a cathode, and traveling to a metal plate in the vacuum tube, the anode, the plus side. What happens is this. Because they are charged negatively and the charge on the plate is positive, they are strongly attracted to it, and the electrons will accelerate toward that plate. All right, so far so good. You will get a diffuse cloud of electrons coming off of the filament and slamming to a stop when they hit the plate. What happens? The electrons lose their forward momentum. They slam to a stop in the plate, and a curious thing happens to their energy. It turns into photons. It is released. And these photons are X-rays. So you literally can take a vacuum tube, spit electrons out of the filament, slam them into a highly charged plate, and get X-rays shining out of the end like a flashlight. That's how you generate X-rays in an X-ray tube. And that's been around since even in Nikola Tesla's time. He was known to have constructed an X-ray machine that allowed him to see, it's called a fluoroscope, to see the bones in his foot or in his hand, and he used to X-ray himself all the time. We only know how much damage that might have done, and yet, it didn't seem to result in cancer. However, it normally can. So now, here's the interesting thing. If you take a beam of electrons and you shoot them in a straight line, and they strike a metal foil, an interesting thing will happen. Some of the electrons will undergo what's known as an elastic collision, and some will undergo an inelastic collision. Now, physicists always talk about collisions in one way or another, and elastic and inelastic are the two most common methods of describing how something collides with something. What does it mean? When they talk about an elastic collision, what they're saying is something didn't break, it bounced. Just in very simple layman's terms. Let's say we explain this to a 6-year-old. In an elastic collision, something bounced. In an inelastic condition, something broke. So in this case, if you shoot a beam of electrons at some matter, such as a crystal or some foil, what will happen is many of the electrons will reach the atoms in the foil and will bounce off of the electrostatic field around them, the field of electrons. Now, this is what happens in an inelastic collision with an electron. It will change direction. It will scatter in some direction, but it will retain all of its speed. So it doesn't give off its photons. It is literally deflected softly like a Nerf ball, sort of. All right, fair enough. We can understand what an elastic collision with an electron would be. And you can put detectors all around an object, and you can see if there's a preferred direction for the scattering of the electrons. This gives you kind of a low-resolution picture of what atoms look like using electrons as the light source. Now, if you have inelastic collisions, what happens is the electrons penetrate inside the atoms and ionize an electron on the inner shell. When this happens, some of the energy is transferred to the atom, the electron slams to a stop, and the rest is given off as X-rays, typically. And so you can take a sample of metal and you can get a pattern of X-rays shooting out the back. They are scattered. But this is where something interesting happens. Under certain circumstances, for instance, if you have regular arranged atoms such as a crystal, you will get regular patterns in the scattered electrons. And they're easy to see if you use a fluorescent material. It could be a phosphor screen like the old oscilloscope tubes or an old television tube. There are many ways of making this show up. But when you scatter the electrons in a crystal, they will give off an amazing pattern of crosshatch or dots that correspond to the structure of the crystal in the material. So it tells you how the atoms are arranged in the crystal structure. This is called X-ray diffraction. Now, scattering the electrons gives you a diffuse glow, and the inelastic collisions are the ones that give you the crystal markings that show up with the distribution of the atoms. So the electrons are scattered in two distinct ways. The elastic ones come off as a soft glow in all directions, and the inelastic collisions give you the sharp peaks and waves that show you where the atoms are located in the crystal. So that's a type of scattering as well. Now, the scattering ends up being ordered by the atoms themselves, but it's called X-ray crystallography, and it allows you to see the structure of new materials that you've never put together before. Let's say when they made the new superconductors, they didn't know exactly what they were made of or how the crystals were arranged. And the early man-made superconductors, the earliest ones that were high temperature, were made of yttrium, barium, copper oxide. And that was an interesting material. I won't get into superconductors tonight except to say that it's a special material, and in almost all cases so far, they have to be chilled very cold, at least at the temperature of liquid nitrogen, sometimes liquid helium, which is much, much colder. And it makes an electrical conductor that has no resistance to the flow of electricity through it. And that has some very interesting properties. We might talk about superconductors at some point in the future. But it happens because the inverse of scattering occurs. The electrons in them pair up. They're called Bardeen-Cooper pairs. And Cooper pairs move through and have a minimum energy, and therefore the resistance tends to disappear. And by the way, Bardeen and Cooper in this case are two of the people who worked on the initial transistor, the field effect transistors. Shockley, Bardeen, and Cooper, if I believe I'm right. They made the first transistor. And again, in that case, they didn't want scattered electrons, they wanted orderly movement electrons. So, scattering. Random movement can actually yield something for you. There's a third quick case I want to tell you about. Sometimes when you're trying to study something, particularly quantum mechanics or wave functions, and you don't have clean data, you have noise in your data, scattering can allow you to do what's known as the Monte Carlo method, which is literally like gambling. You throw the dice, you see what happens. And if you have a certain bias in the data or a set of the data, and you do these random number generations, you can reveal trends or predictions. And it's a method that a lot of computer programmers started using early on. The first one that I know of that used it was John von Neumann. I mentioned von Neumann machines that can eat rock powered by sunlight and make copies of themselves. This was the fellow back in the early days of computing in the 40s and so on, who thought about this wondrous machine, and we're getting close to making those very soon. So scattering is an interesting concept. The fact that you can throw random motion into something and somehow you can gain a solid answer. And again, many times it takes millions of samples. If you were doing the pi issue, as I mentioned, where you throw a bunch of darts at a field and then you count how many are in the circle and how many are out of the circle, in this case, you literally have to do 1 million samples in order to get 3.14, just the first couple of digits of pi, reliably. So it's not a great method, but it does work. And given time and patience, you can actually get an answer out of it. And as for scattering with electrons, it's become a big business for crystallography, for analyzing materials, generating X-rays. Now, scattered electrons make scattered photons up in the X-ray band when you do that. And if you ask your dentist next time you're getting an X-ray of your teeth, what the voltage is on an X-ray machine, he might be delighted to say, "Oh, well, it's 300 kilovolts, or we're doing it with 50 kilovolts, or whatever." And so he'll give you a voltage number. That voltage in kilovolts, thousands of volts, is the energy that is used, the energy level used to accelerate those electrons. And keep in mind, in the wiring in the wall of your house, the electrons are only at an energy of about 120 or 220 volts usually. If it's any more than that, you're probably not living in a house. Well, anyway, if anybody has any questions, the floor is open. Meanwhile, I'm going to urge you, please go to Schultz Laboratories or Universe Science Center, sign up for the classes, sign up as a member, join us live on the randomizer, bring us your questions, your ideas, and anything you have in mind, and we'll talk to you live on the air while we're doing this show. And I always look forward to interacting with people. We've gotten some pretty interesting questions over the time, and we continue to do this. And by the way, my original podcast, Talk Universe, and if you want to see the site, it's talkuniverse.org, is going to be returning soon with full video, and we'll have live call-ins. We just got our new phone call-in mixer panel, and we'll be hooking that up so people can call on the phone if they want to listen just to the audio, and you can see the thing in full video, all its glory, my terrible looking hair, and enjoy the show. We'll talk for about 45 minutes, 30 to 45 minutes. I think an hour is a bit long for it these days. Most people don't have the time to spend on something like that. But if we do 30 to 45 minutes, I think that's much more reasonable. And it probably will return about Wednesdays, 9 p.m. Eastern Standard Time. That's just off the cuff plan. So yeah, join us for Talk Universe when it returns. And of course, everybody who's a member of Schultz Laboratories or Universe Science Center gets all of the Talk Universe insight and all the other things for free. Your members get perks. That's the way it should go. So anyway, thank you everybody for showing up for tonight's talk about scattering, or scatter the term. And we hope you have a wonderful weekend. I have a quick quote for you. Yes, I'm going to get religious on you. Tough. It says, "Therefore, if the Son makes you free, you shall be free indeed." And that's from John 8:36 in the New King James Version. I don't know about you, but I prefer the New King James Version of the Bible. It seems a little closer to, I don't know, I'm probably entirely out to lunch here, but I've always heard it that way as a kid, and that was the one I always learned from. So I read the Bible when I was about 8 years old, and I have to tell you that it stuck with me, and it helped shape my morality. Anyway, everybody have a wonderful weekend, enjoy yourselves, and do the one thing I always encourage everybody to do: make the world a better place. Thank you and have a great evening.